Okay, let's put in our dots now for the second data set and compare what we get. So you could think of this as some different researchers also tested these 3 drugs maybe, or maybe it's 3 different drugs. It doesn't matter. I just want, basically we want to compare what the dots look like. Okay, so let's put our dots in. For drug A, we have a dot at, and you can't see the number line. There, okay, that's probably as good as it's going to get for us, seeing everything all at once. Okay, so drug A has a 14, 2 2s, and a 7, and a 0. And then the mean, which I'll put below again, just like we did in the last one, the mean for those is a 5. Let's put in the dots for drug B. Drug B has a 10, a 3, a 15, a 7, and a 5. And the mean for drug B is 8, so I'll put a dot underneath the 8. And then last, drug C, I'll put that in green. Drug C has a 6, a 7, 2 12s, oops, just 1 12, sorry, and 2 15s. And the mean there is an 11, so I'll put a green dot. Oops, boy, making problems with this green. Okay, so a green dot underneath the 11. Now, if you look at these dots, boy, the 3 samples, they're all scrambled up with each other. So it's not clear. It doesn't look to me necessarily like they come from 3 really different populations. There's no clustering. There's no separate clustering of one color from another. So it's hard to tell. Maybe the whole population is spread out like this, and we just happen to get samples. The red one happened to look like that, drug B happened to look like that, drug B happened to look like that, just because we've got small samples. Maybe in actuality, the overall population for A, B, and C are very similar. And again, the spread out population, and we just happen to get these 3 spread out samples that just happened to have those 3 means that are different. So you don't know. And the point I want us to come away with here is that here it's in this first data set, the samples do appear to come from populations with different means. You know, you can't tell for sure, but just looking at it, it looks like you've got 3 very different populations that would have different means, so with different means. On this one, it's really hard to tell. The samples could, let's say plausibly, come from populations with the same means. Okay, so notice there's in both of these the means are the same. We've got a 5, 8, and 11, 5, 8, and 11, but the underlying populations that the means come from, based on the samples, it looks like here they're different. Here you can't tell because they're all tangled up with each other. You know, the red ones go across the board. The green ones, they're shifted a little to the right, but they have a pretty wide stretch. The blue ones, they go mostly across the board, so hard to tell. So to kind of summarize those ideas, if the sample means are more spread out as compared to the spread, or spread outness, but anyway, I'll just say spread. More spread as compared to the spread within the samples. Okay, and again, looking at the dots, what I mean by that, here the sample means are more spread out as compared to the spread outness of each sample. Here, the means are not as spread out as the samples are. So even though, so again, I'm making a comparison between how far the means are spread out versus the spread of the individual samples. The spread of the means themselves is irrelevant. So these three means are spread out in the same way that these three means are, but the sample spread is different. And so comparatively, these means are spread out enough that because the samples are clustered tighter, the means are spread out enough that the samples don't intermix. They're pretty clearly distinct. Whereas down here, even though the means aren't spread out any more or less, because the samples are more spread out, they get mixed up with each other, and you can't tell whether the means of the populations are different. So it's the comparison of the spread outness of the means to the spread outness of the samples that counts. Okay. So if the sample means are more spread out as compared to the spread within the samples, then it's more likely that the populations from which these samples come do not have the same means. Okay, so what we're talking about here is the data set 1. So the picture above is the one where the means are more spread out as compared to the spread within the samples, and that's the picture where we can say with a certain amount of confidence that it's more likely that the means of the populations from which the samples came were not the same. Okay, so let's just finish off the ideas here. So the test statistic for ANOVA, it happens to use the F distribution, which we haven't seen yet. But anyway, you're basically going to take a ratio to compare the between sample variability. And when we say between sample variability, we're talking about the spread between the means. How spread out the means are compared to the within sample variability, and that means what you probably think it means. It's the spread of each sample. Okay, so the dots above the number line, how spread out were they? The dots below the number line, how spread out were they? If the means are more spread out compared to each sample, then you have a bigger test statistic. Let's get a little picture to go with that. I think you have room to the right of that formula in words to let's just see what the F distribution looks like. It happens to look something like this. So we've got a formula for coming up with our test statistic, F naught, and then of course the area, and I mentioned that this is a right-tailed test, the area to the right of F naught gives the p-value. Okay. And notice that, so we said if the means are more spread out compared to the spread of each sample, you're less likely to have the means all be the same. A bigger number up here gives you a bigger fraction, right? Bigger numerator gives you a bigger fraction. So if this was bigger, that would move F naught to the right a little bit, so you'd have less area, less p-value, and a smaller p-value means you're going to, so a small p-value means you're going to reject the null hypothesis. You're going to reject the hypothesis that the means are all the same. Again, that's more likely to happen when this number on top is bigger, when the spread between the means is bigger. Conversely, if the number down below is bigger, you have a smaller fraction, so smaller F statistic would move you to the right, sorry, to the left, so you'd be over here, you'd have more area, bigger p-value, and you'd be then probably not rejecting the null hypothesis. So just as always, we reject the null hypothesis if the p-value is less than alpha. Remember, alpha is also called the level of significance, and it's also the probability of making a type 1 error. And we do not reject the null hypothesis if the p-value is greater than alpha. That's probably a good stopping point, and we'll come back in the next video and actually do an ANOVA test. We'll go back to that researcher testing out medication, exercise, and diet as blood pressure treatments, and do an ANOVA on his data. So I'll see you then.